Good morning, everyone. Thank you for joining Mega Asia webinar. I'm Grace from Mega Hong Kong. Today, our topic is Keep Your Motors Running, presented by Mr. Paul Nock, who is the Renewable Energy, Rotating Machines and Industrial Segment Manager for Mega APAC. This is a recording webinar. You're automatically muted to prevent any background noises. During the webinar, if you have any questions, please type into the question box, which you can see on the left of your screen. We'll answer the questions at the Q&A session. At the end of the webinar, please help us fill in the survey, which is on the right-hand side of the screen. We'll be sending the presentation materials to those who completed the survey. Attendees will be able to download an attendance certificate after they have finished the webinar and completed the survey. And the recording of this webinar will be sent to you in 2 days' time by email. So without further delay, let's start now. Thank you for joining us today.
And welcome everybody to Mega Baker Instruments webinar today on motor testing, as Michael says, but keep your motors running and what tests are important is the subject of today's webinar. So as you can see, my name's Paul Nock, as Michael just introduced. I'm the Baker Sales Manager. Baker, just to give you a very quick overview, Baker is a company that was purchased by Mega about 2 years ago now, but a little bit further history about the company. It was a privately owned company that was set up about 50 years ago, 60 years ago, and we manufacture test equipment that is designed specifically for electric motors. So everything that we do, everything that we present, everything that we kind of talk about is all related to our experiences in the field and our experiences over that time. We were the very first manufacturer of a specific electric motor test equipment. So we're a very nice fit to the Mega network, obviously also being the very first manufacturers of insulation resistance test equipment. So we feel as if we're a really good fit together and a nice home for the products. But this really isn't about the products. This is more about the testing that's involved in electric motors and what is practical and so on. So let me turn my camera off so I don't distract, and we'll get on with the webinar. Okay. So first of all, a little about myself. I've been involved with electric motor testing and testing in general, literally all my working life. I was very fortunate to have a lot of experience working for a service company that not only repaired rotating plant, pumps, gearboxes, electric motors in their workshops, but also they had a very large network of service operations around Europe at the time, but also in Asia and also in the US. So I managed to pick up a lot of experience testing motors in the field in various applications and from various segments. So yeah, I've got lots of experience in and around electric motors in the field, which I think is important, because if there are lots of people with knowledge on electric motors, but not many people that have the experience that I've been very fortunate to gain about testing in the field. So that's why I've put this webinar together to talk about what's important, what are the tests, and what is really practical, because there is so many choices out there of different tests that we can apply to electric motors that it's become a bit messy, and customers in general, the feedback that we've had is that they get a little bit confused of what do I do? Should I do partial discharge? Should I do dielectric absorption? Should I do insulation resistance testing? Should I do surge testing? Should I do X, Y, Z? And the answer is, you know, obviously all of the tests have good merits, but what is practical? And that's a little bit about what we're going to talk about today. But what are we trying to do by testing our motors? Well, we want to reduce unscheduled downtime. We want to predict any imminent failures before they fail, obviously. This is to reduce downtime in the field. and to keep longevity of the plant, keep it in good condition. You know, the ultimate goal, of course, is to save time and money. And it's been proven many times over. And in fact, young people coming through trade schools and engineering university courses now are having in-depth training on condition monitoring and predictive maintenance principles. So there are many different strategies out there, but it does depend on your plant, and it even depends on the type of plant you have. And what I mean by that is, let's say that you have some plant that you cannot afford to break down, and then some plant that you can afford. If it breaks down, it's not going to hurt you. It's not going to create too many issues. So we have to apply a multitude of maintenance strategies across our plant to be able to identify the best course of action and strategy that we have in keeping our plant running and keeping us profitable. So here's a little brief rundown of the different types of strategies that there are. Obviously, there's corrective maintenance, which is basically run to fail. So, you know, the percentage of failures that we pick up prior to that is zero. And if we've got a plant that runs totally run to fail, we can obviously afford to do that. We're not so worried about, you know, having people standing around while the plant is down, or people being sent home while the plant is repaired. Perhaps that's not the scenario. The other thing is perhaps they have enough stock in their system that they can do without their plant for 2 or 3 days. But this is rarer and rarer in today's field. Most people don't work like that at all anymore, and they've got a combination of preventive maintenance, predictive maintenance strategies in place. So it's important to identify what's critical in the client's plant and do a criticality analysis. So corrective to failure basically picks up no faults prior to failure. Preventative maintenance, time-based maintenance. This means we fix it even if it's not broken. A lot of people have, okay, we'll run this unit for so many hours, and then after that we're going to pull it down and service it. Well, that's good, but what if there's nothing wrong? Then you've just wasted time and money. So monitoring it, we'll be able to remove it and test it at the correct time in its life cycle, so that we don't have to waste time and effort removing a motor that doesn't need anything. At the same time, you know, that we may also have one that was going to fail prior to that time-based maintenance, and we've been able to pick it up because we've been doing predictive testing. Condition-based maintenance is the key there. So that's this bottom area is really what we're finding in this industry today. And a lot of the testing principles that we're going to talk about, some of them are not very well known in the industry when it comes to electric motors. Electric motors are often confused between the main mechanical and the electrical disciplines. So if you think about it, it's a merger of the two. We do have mechanical there, but we also have electrical. So whose department takes ownership of it in a typical factory? Usually the mechanical and the electrical maintenance are split, and then we have maybe a condition monitoring team that sits in the middle. So when it comes to electric motors, we have to apply the right tests, the right strategies to identify and to keep longevity of our plant. With a motor system, there are 3 elements. There's the power, there's the motor itself, and of course there's the load. And the load could be anything. It could be a fan driven by a belt through a gearbox onto the motor, and then the motor is supplied by a VFD, which is the power. Any one of these areas could lead to the failure of the system. So we have to apply tests to the entire system to be able to identify areas of failure. But one thing that is evident in the majority of predictive maintenance techniques applied to factories globally at the moment is that when it comes to the electric motor, there's not enough attention paid to the electrical failure side. So one of the things that I'm going to be talking about today is what tests can we apply to electric motors that would be practical and give us enough information that we can plan maintenance prior to failure. This is very important because at the moment, a lot of maintenance crews will say that they do various tests. They do mechanical tests, they'll do electrical tests, but what they mean by electrical tests is they'll test the motor periodically for insulation resistance to ground, or they'll put a thermography camera on the panel looking for loose connections. But that doesn't give enough information on the motor, and in fact it's going to miss 80 to 90% of the failures that we see with electric motors in an electrical way. Yes, of course, electric motors are very prone to bearings, especially the smaller motors. So we have to do vibration analysis and such tests to identify mechanical damage. But mechanical damage gives off lots of warning. It gives off heat, vibration, and so temperature, heat, and noise. Electrical failures do not do this. Usually, the critical failure element actually takes place during startup and stopping of the motor. So then next time it's started and stopped, it's already deteriorated and it starts to be compounded. And it doesn't take long for that failure to occur electrically. So our window of catching it with insulation resistance testing or other periodic tests is very difficult unless we've got a true predictive test. So from an early warning perspective, which is what most customers want these days and what they need. Can we prevent our failures? Well, we can, but we have to include all of the parameters that we need to identify the fault mechanisms that occur in electric motors and their load and their power supply. And once we've identified which tests we need to apply, we obviously have to add them to a PDM program, which would also may also differ. So if I'm doing vibration on a bearing, perhaps I should test that every 6 weeks or every 2 months, because the failure mechanically of an electric motor's bearing is a lot faster than what it would be with an electrical insulation breakdown. So we may stretch our testing of our insulation resistance to ground and between the coils and turns to the winding. That might be done maybe every 6 months. But we need to have a strategy to identify what's the best practice here. Here's a couple of pictures. This is me up in the left-hand corner. I'm conducting vibration analysis on a wind turbine generator there. To the right is a oil sampling. To the right again is thermography, but as you can see, it's only surface temperature that the thermography camera can pick up. It can't pick up winding faults inside the motor because it doesn't X-ray the motor. And of course, ultrasonics, as well as other mechanical tests that we could apply. But you know, these generally cover most of the mechanical aspects that we need with failures of electric motors. But we're still not covering the biggest area of electrical breakdown. Here are some timelines, you know, of where the fault is initiated. Ultrasonic is very early detection of some mechanical issues, vibration, then thermography. So maybe the motor starts to heat up, but this is already well down the path of failure towards of the electric motor. So a lot of these issues aren't really very predictive. They're kind of almost protection. So as soon as we get an alarm, we have to turn the unit off or plan immediate servicing, which isn't really practical. We'd like to be able to detect it far earlier in these cycles to be able to identify faults. We do have electrical test equipment that is designed specifically for this process. What you're seeing here is on the two instruments on the left are basically instruments that look at the power supply and the operational, the system as a total, as well as the performance of that system, its efficiencies and things like that. So this actually monitors, even though they're electrical testers that one's a portable unit that picks up currents and voltages, etc., via CTs and PTs, etc., and the other is a permanently mounted system that has a Wi-Fi connection that sends the information to a monitoring system that can be alarmed and warn the operator that there's an issue with any motors or loads or power supplies. And then on the right, these instruments are designed at looking at the insulation systems within an electric motor, and we'll go into more about that. So there's two types of electrical test that is not considered, well, is not very common in the marketplace at the moment. We do have many opportunities to introduce this and to present this type of information, and have been for some time, and so have our competitors, to be fair. But the truth is, when it comes to electric motors, they're still considered a little bit of a dark art or a mystery, and don't really want to get involved. But they know, i.e. Our customers and our distributors and even our own people, need to know the framework behind the applications, the types of fault, and where these systems are best introduced to the test cycle. Obviously, the one on the left is a permanently mounted system, and it's continuously monitoring. So that can give us good information and identify failures of the plant well ahead of actual failure. The periodic testing or condition monitoring on a time-based maintenance. So maybe every month we'll go in with this instrument here, and we'll monitor the performance manually if we're not doing it online. And then the last one is a system that again is manual, but you would operate this from the MCC, looking at the motors in the field, testing them on a periodic basis. Again, giving yourself the frequency of tests that would identify any faults well ahead of failure occurring. So this type of equipment is necessary to identify many of the failures that we get with electric motors. I'll skip through some of these. This obviously is an electric motor. You can see there that we have windings. We have it's very mechanical, and the windings on an AC motor are very simple. They're just a continuous loop of wire wrapped around some iron, which creates poles. And then as the three phases increase and decrease with power, so like the red phase, when that's at its peak, then, you know, in the cycle, the blue phase comes in, the yellow phase, and that kind of powering up and powering down of the different phases and the different poles within each phase creates a rotating field within the electric motor, which the rotor just catches to and tries to follow. So that's a very simplistic way of looking at it, but the insulation system on these windings and turns is critical. And this is where, and it's the weakest insulation in the motor, is between the turns and the coils, not to ground. So insulation resistance would test for moisture and contamination maybe, but it wouldn't give us the predictive element that we need when relating to the winding failures due to deterioration of the turn-to-turn coils and the coils themselves. This is obviously what we're trying to avoid, and this is very common. Once we have shorts and burnout happening in the windings, the heat internally to the motor becomes to a point where it would melt, trip, etc., depending on your control system, but it would create massive problems for the motor and probably lead to a scrap situation with the motor. Here's some breakdown. This was by GE, and as you can see, motors that are small, less than 4 kV, so these are the rolling element motors that are very common. You can see mechanical is a very common issue, but still electrical is also still very common. Once again, we are able to identify mechanical issues very easily, but it's the electrical side that we have problems with. And then when we step up to the really big motors, they very rarely have rolling element bearings. They often sit in oil style bearings, so there's no friction. And so obviously mechanically, there's a lot of issues that don't appear on that type of motor as a rolling element bearing motor. So you can see the electrical failures of the stator are much more prevalent in the higher voltage range than the lower range of motors. This is a breakdown of all the motor failures that we could think of, basically. If you think about any type of failure from contamination on the bearings, coupling issues, air gap faults, et cetera, right the way through, as much as we could work out, we actually thought, well, what tests could we apply to all of these different failures to identify what the best condition monitoring practice would be? And we actually color-coded it to these 6 areas. So offline electrical testing, online electrical testing, temperature trending, vibration analysis, visual inspection, and oil analysis. So really only 5 tests there, apart from visual inspection, that could pick up a lot of these issues. So there's not that many technologies we need to have the power to give our electric motors the best longevity they can. But we just have to apply these technologies for these various identification of failures to be able to do that. So let's go back to a little bit to the basics, motor problems. Electrical, obviously, is very expensive because it's difficult to identify failures. Once a motor's burnt out, if you haven't got one in your store and you have to get one, and let's just say you can't get one because there's something unique about that electric motor, which is very common, then you have to wait. So that means a lot of downtime, especially if the damage got to the point where the local service company and rewind shop can't repair it because the damage has gone too far. And mechanical, we have lots of different ways to, and established ways that we apply condition monitoring, such as vibration analysis. So this is something that is really important when it comes to testing the windings. A lot of people assume that the insulation resistance test is almost all that we need to do, and a polarization index, let's say, or even a step voltage test. But they're all different forms of conducting the same insulation to ground testing. The weakest area of the winding is between the turns and the coils. And this is because the insulation between the turns and coils is that thin, it's just a thin layer of enamel varnish that is preventing these turns from shorting to one another. So we need to test both insulation systems. And as you can see, the insulation strength here is 32,000 as opposed to 8,000. And here's more information, but we actually got a diagram here. And you can see how thick that card is. That's the insulation. And it's usually a Nomex, a Polynomex kind of composite insulation. So it's got the plastic in there for strength, and then the Nomex, which is quite a papery substance, on either side of that plastic to give it strength and insulation. But its rating is very, very high. It's usually around 30,000 volts. The insulation on the enamel of the windings is much, much lower. So that's the weak point. What can damage it? Thermal aging, contamination, mechanical, overvoltage spikes from starting and stopping. Obviously, starting and stopping is usually the harshest environment for an electric motor. It takes a lot of current, almost 8 times full load current. So if you think about the motor when it's in operation, the maximum we can get out of it is, let's just say, the full load, the current would be rated at 100 amps. Well, on startup, it will probably take something like 700 amps. So during the startup process is the worst it can see. But that is compounded by spikes of voltage. Because when the contactors come in and they have contact bounce, you get these spikes of voltage, which is often 4 or 5 times higher than supply voltage. So volts times amps equals power. So we've got massive current, 3 times the supply voltage. That's the worst area that a motor will see. So we must be able to do our tests looking for weaknesses that would be exposed during those startup procedures. Here's some pictures you can see here. These are typical and I've seen this many times. I don't think I actually took these pictures, but when I worked in the motor shops, when we actually take the guards off a motor, this was very often the scene that we saw. So the insulation to ground can often happen in the slot and is often with the motors compounded by contamination and moisture. Here are some faults that you can see, but what is the root cause here? What often happens is as the insulation comes out of the core, the coil itself is wedged and is very strong and it's then varnished. But when the outer ring of the windings on startup and stopping flexes, now we varnish it and we tape it and insulate it to try and keep it as tight as possible, but it's always moving. And what happens is if you start to get movement here, it starts to break down the insulation systems, not only to ground. Ground is usually the final area, but it's the insulation between the turns and coils that start arcing that lead to this breakdown and then the flashover. So these are all too common, and they're usually found on the overhang of the windings because that's the weak spot. How can we identify this? Well, we can test turn to turn. And how we do that is we've got a test in the Baker products called the surge test, apart from one of the suite of tests that we have in the instruments. But the surge test doesn't look at ground insulation. It just looks at sending a pulse of a capacitive pulse through the winding, looking at the potential difference between the coils, trying to create an arcing between that potential difference. But there's very low power in this test. It might be high voltage, but its joules energy rating is very low, much lower than what the motor would see during startup or it's fractional. So we try to emulate the voltage at startup. If it's a 400 volt during startup process, we might see a 3000 volt spike. So we'll try to emulate that along with the standards. Maybe it's IEEE or IEC standard that we apply. But whatever happens, whichever one we choose, we have to apply and emulate what the motor sees in startup to try and identify faults with the windings. And this is like a life expectancy of a motor here. So in this example, you can see 1981 to 1998. So this motor lasted 17 years. The insulation between the coils and turns was rated at 8,000 volts, but over a period of time, due to movement, heating up and cooling down, the very thin insulation on the turns and coils starts to break down. When it gets to the point of reaching our starting and stopping spikes of energy that you can see here going along the bottom axis, once they reach this insulation breakdown curve, what happens is a huge arc inside the motor, and that will carbonize. And okay, the startup process is very quick, but what it starts to do is create next time it starts up, an easier path for an arc and a short, until eventually it deteriorates to the point where it becomes a permanent short. As soon as that becomes a permanent short, that means that the winding has failed, and it will burn out in seconds. Because what happens with a shorted turn, it's like having a copper ring inside the winding. It just heats up and heats up and heats up until it gets red hot, and then starts a chain reaction of burning through the coils insulation between each other and then through the ground insulation. And if we wanted to look at studies on this, you can see here we've got this was Phelps Dodge. So this was a cross-section of a fairly new motor, and as you can see, the insulation there on the wire, the enamel varnish is very thick, and here you can see it's thinning. And over a period of years and time, with this flexing and this movement, this will become thinner until arcing can start to occur, and the electricity can skip a few turns because it's always trying to find its fastest way of least resistance. So if it can skip a few turns, it certainly will. So the question is not if a motor will fail electrically, it's just when it will happen. So therefore we have to monitor it to identify. So what tests are really practical? So for general plant, we went to some organisations like IEEE, ESA, IEEE, IEC, I think NEMA, and a few other organisations. And during those conversations, we said, okay, well, what tests do we need that would give you enough information to have the comfortability or confidence that the motor is not going to fail? And we could have added many, many tests here, but don't forget we were trying to keep it practical. So if we said, okay, we're going to add partial discharge here, then that takes up more time. And is it going to identify anything that some of the other tests couldn't do? We could have done various tests in the same way. So the feedback that we got was, because we wanted to create an instrument that had all of these tests in one box, in one software, so that that we could retrend all of the results and look for deterioration with multiple testing over time. And this is what they and us came up with, and this is what we've applied in our instruments to this day. What does that do? Well, we have a winding resistance test. What does a resistance test basically do? It tests to see if we've got continuity. It tests to see if we've got an open circuit, and it'll test if we've got balanced levels across windings. But is there any predictive maintenance there? No. What it will tell us is, like I said, if there's already a fault, it's not going to give us any predictive. Same with the mega ohm to ground. It's going to tell us whether it's safe to switch on. It's going to say, is it contaminated with water? Is it less than 1 mega ohm to ground? If it is, then it's unsafe to operate. But the insulation to ground could be temporary. It could be contamination, or like I said, it could be moisture and it just needs cleaning, and it might need drying out, and then the insulation will return to its former self, and it would be strong again. Polarization index, step voltage, these are other ways that we can look at ground test. Now we can increase the voltage, still look at the mega ohm levels, and still look at the stability over a 10-minute test of polarization index, looking for deterioration. But really, if it's a nice stable reading, then we'll expect from 1 minute to 10 minutes that the mega ohm level will at least double, which will give us a polarization index of 2, which is our minimum acceptable level. And then we have high pot. High pot is it has been changed over recent years to be better used as step voltage. Step voltage enables the voltage to be increased in steps rather than just ramped up. And by doing that, we're able to see the current leakage settle down to a steady level. And we can then tabularize that information, looking for linear in not only the insulation to ground in a way of mega ohm, but also the current leakage and also the different voltages that we have. So we're looking for linearity and a steady table. That will give us the confidence that the insulation in our motor to ground is stable. Then we have surge test. Now surge test is, like I said, it doesn't look at ground insulation, and it's why the testers are as big as they are, because the capacitors in the back fire a pulse through the winding, looking for this potential fluctuation of the sine wave that will indicate that we have issues with between the turns and the coils, which will be exposed during startup. So what does a mega ohm tell us? Well, like I said earlier, it determines if the motor has already failed to ground. It tells us a little bit if it's contaminated. The polarization index and the absorption test, which is similar, just really looks at the same levels of the insulation to ground, but from a stability point of view. It cannot determine if a motor is good. It will not tell us if the motor, once it starts up, it burns out within 5 minutes. So it won't find a turn-to-turn volt, it won't find an open phase, and it won't find a phase-to-phase fault. When we look at polarization index, you can see the megohm level in black, usually over a period of a 10-minute supply, increased to a nice steady level. The leakage to ground deteriorates with that increased megohm level, just like Ohm's law. So what we should see after 1 minute, where you can see my cursor here, between 5,000 volts here, sorry, 5,000 megohms to 1 minute, we should see that after 10 minutes, it's increased in a nice steady way to be at least double, and then it's passed the polarization index test. So that's how we work it. But really, we're just looking for stability. We don't want to see any fluctuations and spikes, because there must be a reason for that. So it's usually because of unstable, brittle, hard, dry rotted insulation and maybe some contamination as well. So this is the difference, what it looks like. So as you can see, the blue there is the applied voltage. So instead of just ramping up constantly, where we get one set of readings, by doing it carefully, it allows us our microamp leakage to settle, and we can trend that. And we can also trend the megohm level as well. So by trending both those, it gives us the opportunity to have more confidence that ground wall insulation is strong or weak. But the surge test is the only consistently reliable method of detecting weak insulation between motor turns. Still to this day, the instruments themselves have changed a lot. They are now much smaller, they're portable, and we can do these readings out in the field. Even when I was a young man and apprentice, the equipment was just so large, it wasn't portable. But nowadays, we've got instruments that have PCs inbuilt into these instruments that enable us to trend results, send emails of alarms, etc., etc. So the technology has really come on a long way. What can surge test do? Yes, it can find turn-to-turn foils, phase-to-phase issues, coils, basically winding faults. But in the field, it can also tell if we've got reverse coils, unbalanced turn count, different size copper, shorted laminations. These aren't very common, especially the shorted laminations. Usually it's because the motor has already had a significant failure, and that has led to shorting between the laminations of the core. So really it's looking at the inductance change of that particular phase area against the rest of the motor. So this is what a good surge pattern looks like. We've got two graphs here. The top one is the finished pattern, and what you will see during the test is it will increase the voltage from 0 up to 3000 for all three phases, and we're looking for stability and balance across the three phases. Down here, we're looking for, this is each one of the pulses of the capacitor. So we're looking for the reaction against that pulse, and we want it to be consistent. So if there's any fluctuations or issues with the insulation between the turns and coils, we'll start to see these fluctuate. Sometimes we do get a little bit of imbalance on this, but if it's combined with a very good pulse-to-pulse, we have to question whether maybe it was the rotor in the motor, if it was still assembled, that was leading to a little bit of phase shift or inductance difference there. But really, if we had an issue, it's very, very obvious. This is one that's starting to deteriorate. Even though the full test between the phases is balanced, we're starting to see here that with each pulse is starting to be fluctuating a little, and we're starting to see some spikes of the results on the PPAR. So this is where we can start to determine the earlier predictive element of the unit. And this is a failed one, obviously. So the red phase there and the yellow phase. The blue phase has obviously passed the test, but you can see on red phase and yellow phase, we've got serious issues with the windings there. And what does that look like? Well, it could end up like this. What happens is, if you look at the left and slot cross-sectional area there, you can see that the insulation is totally encapsulated in the windings. The windings are in good condition. During startup, perhaps this turn-to-turn issue has started to become a little bit of arcing between the coils and the turns. And each time that happens, it increases. So it gets hotter and it gets more carbonized until eventually it will break the insulation to ground and it will fuse and burn. And when we walk up to the motor in the field and we put our insulation resistance tester on it, we'll say, oh, it's blown to ground. It's failed to earth. But that wasn't the root cause. The root cause, 80% to 90% of the time, is this turn-to-turn insulation breakdown. Now, only the surge test can do this. So if we really want to look at the biggest area of electrical failures in electric motors, then we need to apply the right tests to identify those. So we need to apply resistance, looking for open circuits. We need to apply the insulation ground testing, looking for safety and breakdown of the insulation to ground. And then, of course, we need to look at the winding insulation themselves to get a true full picture of the motor's condition. There are various organizations that we kind of follow and we work with when we're looking at testing electric motors. Here's a few: IEEE, ESA, NEMA, IEC, but there are many different types of organizations that we have good relationships with, but we also follow their guidelines with our instrumentation as well, and even recommend them as well at times. We also have our own recommendation guidelines, but it really doesn't matter. As long as the customer and the motors are being tested in line with these organizations, then we shouldn't see any issues with the testing whatsoever. And we can then trend according to the standards and looking for the deterioration levels. So IEEE, IEC, NEMA, and Baker, they basically, for universal motors or motors in general that are tested, there is a rule of thumb. And because I've come from the industry, that rule of thumb is you should test ground insulation on an electric motor and between the turns at coils at twice the working voltage plus 1,000. And this is something that Baker implemented when they introduced the very first electric motor test equipment, and it's kind of stuck. IEEE have different standards to IEC, and we're somewhere in the middle. But really, what we're saying is it's an easy calculation, twice the voltage plus 1,000. So if we've got a 415 volt motor, we should be testing that at 1,830 volts. Remember, that is still much less than the motor sees in the field. And in the field, it'll also have very high currents going through it, as well as these voltage spikes. So the testing is only trying to emulate what the motor sees during startup, where most of the failures occur, to give us a clue and trend any weaknesses and deteriorations. Here are some of the standards if you wanted the numbers. 522 is related to surge, IEEE 43 is related to ground, and I think 95 is as well, and so on and so on. Here's an example of why it's important to include all of these tests. Now, if you look at this report, the insulation between the faces is 0.81 ohms. So it's balanced, perfectly balanced, and the insulation is 8,373 mega ohms. That's the resistance to ground. So if we had a insulation resistance tester and we tested this motor, we would say it's absolutely fine. We could go one step further and do a polarization index test. And after every 15 seconds or so on, we could record the results and make sure that and plot a graph that shows that there's no instabilities there. But when it comes to the surge test, if we had a motor that had a winding fault between the turns and coils, then how would we identify that with an insulation resistance tester? We wouldn't. So therefore, we have to apply this equipment with this type of test. And as you can see, A and B went through their full tests, phase 1 and phase 2, no problem. When it comes to the third phase, the test, as it increased its voltage, got to 1,000 volts. Instead of reaching here at 1,500 or 1,800, this one, when it reached 1,000, it started to fluctuate. So the tester stopped the test and said, "Oh, we detected some issues here. We need to investigate." So that way, this motor could continue to operate, but if it had any issues with the, we've identified that there is an issue there. The motor could continue to operate, but because we know it's got an issue, we can plan maintenance around it. Remember what I said. So if the supply voltage was 415, because the insulation strength between the turns and coils is rated at 1000 volts here, we know it's not going to be a solid short when it starts. So therefore, we can say to this customer, okay, what this testing instrument is telling us is it's failed the turn-to-turn coils. We need to limit the startups if we want to keep it running to a certain date before we can replace it or get it serviced. Maybe instead of switching it off after each shift, we should leave it running so that we don't have to expose the motor to those big, high starting and stopping surge currents. And for those of you who know our equipment and look at our old style equipment, this is what it used to be. So we used to have a solid oscilloscope here, and then with the picture at the below, when we start to see arcing occur, that's when this sine wave starts to fluctuate and gives us the idea that we've got winding faults. Very quickly, the last one is a insulation to ground. This is a step voltage. So as you can see, what I was talking about earlier about stability of results. So even though we're going through a high voltage range and looking at ground insulation, when we've got to 8,000 volts, this was a high voltage motor. When we just got past that, there was a big difference in current leakage and a real drop in the megohm. Even though it would pass, it's been able to identify that the insulation is not stable. We can see that there's something happening there. So we can, again, plan this to our advantage before a failure occurs. This is a typical report. And once again, you can see that in this example, resistance and insulation to ground is very good, 124 megohms to ground and a balance of 0.02 ohms. But once again, the phase has failed on B with surge. So it's the coils and the windings that are breaking down before the insulation to ground. So we must include all three aspects of the insulation systems to the test of the motor. Practical, it's not very practical to test motors in the field in general. It takes up too much time. They're usually covered. They're usually put in horrible places. So testing from the panel is a very practical way of doing it. If you can look at this example here, there's an MCC room there of about 5 or 6 motors. I've tested all those motors in the space of, say, an hour. And, you know, if we were to test these motors in the field, it would have taken probably a week. Or even this one motor would have probably took a couple of guys all day by the time they got the covers off, etc. So testing from the MCC is very practical. Another example, this was a power station in Malaysia on the left. On the right was a Filipino power station. And I can't remember the top right picture, but you know, it's much nicer and easier to test in from these areas than it is at the motor itself. So in summary, is it possible to predict a motor's condition? Yes, but you have to apply the right tests. So this is what saves us money and reduces cost. So that's the end of the presentation. Thank you for giving me your time today, and please let me know if you need anything. At the beginning of the presentation, I'll just skip past now. I'll bring you to my email address, which you're more than welcome to contact me on, paul.knock@mega.com, and I'll go to questions.
All right, it comes to our Q&A session now. If you have any questions, you can type in the chat box on the left-hand side. Our panelists here will answer your questions. And for those of you who are leaving, please remember to help us fill in the survey, which you can see on the right-hand side. And we'll be sending the presentation materials to those completing the survey. And also, before you close the webinar, please don't forget to download the attendance certificate, which you can see at the bottom control panel. There's an icon on the right-hand side. So we'll spend about 5 minutes to answer our questions in the chat box. And we're happy here to have Mr. Ronald Pina, Mr. Bernardo Apuya, and Mr. Michael Evangelistas as the panelists to answer our questions. And just a reminder, we will be having another webinar next Monday, 22nd of May. Time is 3:30 afternoon. The topic is Earth Testing Simplified. Which is a webinar conducted by the Middle East team. And also, there's another webinar next Thursday morning at 10 o'clock Hong Kong time. Topic is overview of solar PV installation testing for safety and efficiency. So if you are available next Monday afternoon and next Thursday morning, please go to our website, www.mega.com/webinars to sign up for the webinars.
Can you hear me, Grace?
Yes, Michael. Yes, I can hear you.
I will try to answer some questions.
All right, thank you.
So, questions that I can read from here is that how can you test DC motors in the field? Well, when you are going to use our Baker tester or Baker instrument, we do have accessories for DC motors, sir. So we can test the rotor bar, we can test the armature. So we have different accessories. Depends on your available DC motors. But I suggest you check our website for the datasheet so that you can select. Or maybe what you can do is send us an email and give us some specification of your motor, and we will recommend the accessories that you'll be needing for the test. Okay, so another test here, what is the danger to winding from the surge test? Actually, sir, I'm not sure what other brands that do surge testing, but in our case, in Becker Instrument, we do low energy surge testing, so it's not really harmful for the winding. And it's no danger with the low energy surge testing. All right. So here, another question here. How to select the test voltage for different types from form versus trans winding. We normally, sir, select, or the industry standard is ×2 of the rated voltage plus 1 kV. That is how we select the test voltage. But actually, it depends on the standards that you want to apply. But normally, with the industry standards, we select the test voltage based on the nameplate, which is we need to multiply it by 2 and then add 1 kV. Okay? So another test here, if you do surge test from the MCC, does the inductance of the cable become too high to detect the fault? Actually, sir, when you do the surge testing from the motor control center, of course, you need to consider the cable. So you need to consider the capacitance of the cable, and that will really affect the test result. So when you are on the field, we suggest that you need to do the pulse to pulse uh, error area ratio, pulse to pulse, not lead to lead or line to line, because line to line, there are some effect of the test leads or the cable length. So we normally choose the pulse to pulse, wherein we do step voltage and then we compare the sine wave. Then we compare the sine wave of the surge testing. So we normally do, if we are connected to MCC, we do pulse to pulse testing, not lead to lead or line to line testing. If the motor fails the test, can it be used in servers for some time until replacement? This is difficult to answer, sir. Of course, for me, if you're going to ask me, depends on the failure. So, for example, if your failure is turn to turn for, which is the most common, I prefer not to use the motor anymore. Why? Because it's turn to turn fault is very quick. I mean, very fast. It will escalate to some other components of the motor, so it will easily fail or it will immediately fail. You can watch the video of the actual turn-to-turn fault simulated in. I think you can also find that in YouTube. That once you got the turn-to-turn fault, oh, it's very quick. The motor will fail immediately. So to me, if the motor fails, it depends on the parameters or it depends on the failure that you're having. But to me, if it is turn to turn fault, then it's very critical. Okay. Another question. Oh, we get a lot of question here. Uh, what else? Regarding testing the motor from the panel, how it will guarantee that the measurement is not interference by the cable condition or other. Mm, I'm not sure of the question. Maybe he is trying um, to refer on the noise. I'm not sure. Can you give or can you elaborate more the question, sir? Sorry. Another question: can repeated megar and hypa testing damage the insulation over time? The question is, can repeated megar and hypa testing damage the insulation? Well, actually, sir, the principle is that if you do hypa testing on a very old insulation or maybe already damaged insulation, that could be harmful, of course, because this will intensify. This will damage further the insulation, the high pot. But actually, you need to examine the number of joules, how much pressure, how much energy are we applying when we do high pot. That's the that is the thing, right? We need to check how much joules, how much energy if we do the high pot. There are high pots that is low energy, and that could not also. I mean, uh, yeah, it will damage, but it's not really what do you call that? A big damage because the energy is too low. But there are high pot, that high energy high pot, then that will really damage the insulation. Another question: where can I find the documentation for interpretation of surge test result? Send me an email, sir. Um, I will give you some documentation about the surge testing. Okay. Uh, when testing DC armature, should we use PP or LL test to compare the commutator? Uh, this one I'm not sure. So sorry. For the armature testing, because we normally compare, as far as I know, we are normally compare the resistance. Um, but you are trying to refer on the surge testing here, the pulse to pulse or line to line test. Well, I will give you more information about the DC armature tester. Uh, Let me get your contact number from or contact email from our from Grace, and I will send you the email, sir, about the DC armature testing. Okay, so you can have more idea on the DC armature testing. So I guess, Grace, that's all I
Yes.
can answer for now.
All right. Thank you, Michael. Thank you very much for your support. So if you have any more questions or follow up with your questions, you can send us email to megahongkong@mega.com. We will answer your questions by email then. So thank you again for attending. Thank you, our panelists, Michael, Bernardo, and Ronald. And we hope to see you again next time. Thank you, everyone. Bye-bye.
Thanks, guys.
Thank you,
Bye-bye.
everyone. Bye-bye.
Thanks, Mike.